I'm setting up the live stream now. And I'm gonna let everybody in.
So do we have a link? Do we have a link? Oh yeah, I have a link. I copied the link. So I think Hop probably can do that. Let me see.
Okay. Here's the link. Put it in the chat.
Yeah, I think I also copied it. Let me check whether it's the same. But I can see it.
That's the link.
Okay, good.
I'm gonna admit everybody. Thanks for reminding me of that.
Thank you.
So here comes everybody. There'll be more people coming in. So somebody else, hopefully one of the, good morning. Hopefully one of the co-hosts can also watch the waiting room to keep admitting people. Just have to hit the admit all button as people come in. I think any of us can do that. So welcome everybody. Good morning, good afternoon, and good evening, wherever you are. Let's see. I'm going to, oh, here we go. We're just letting everybody in. We're going to get started in a minute or so. I guess I can run through a few different just brief logistics. So we are going to record this session. We have a YouTube live stream going as well, which you can access later. And we're also going to mute everybody. We're trying to keep everybody muted. And so please also remember to mute yourself if you're not actually talking. And also for bandwidth considerations, people should probably turn off their video unless you're the actual speaker or when we get into the discussion session.
Is that you?
No.
Why aren't you up there?
Let's mute everybody. Okay. So then we're going to actually, the talks is, if people have noticed, or we have a central set of presentations. So the speakers can basically just ask to advance the slides as we go through. This is to try to keep everything on time so we don't have problems with screen sharing. And the moderators will try to give everybody a 2-minute warning for the longer talks. Obviously the shorter talks, try to keep it as short as we can. And then there is the possibility for annotations if you have a recent version of Zoom. That should show up once the screen is being shared. You should have the option for that. And if the speakers want, they can actually make some notes on the slides. We would suggest you use the regular draw tool, and then you could erase it, just make marks on each slide as you go. I think that's about it. For the questions, we're going to ask that you put questions in the chat. We're not going to actually unmute people. Oh, great. Thanks, Dan, for starting up the screen sharing. We're going to start slides in a minute. We're going to, so we're going to use the chat, and the moderator will ask questions of the speaker, 1 or 2 for all talks. And then in the interest of time, speakers can answer extra questions in the chat. And then for discussion, we will open the mics and allow people to talk, but please use your raise hand feature. We will watch the list of participants and try to call on people. It's just we have some order to the discussion because we have a good group of people. We're up to about 68 people right now, and that'll probably grow a little bit as we go forward. I think that's about it. Did I miss anything? Matt or Danny or Mingwei? Oh, I guess I have to, yeah.
Well, I would just remind that people are invited to augment their talks in the when they deposits their extended talks, and that link should also be advertised.
Yeah. I think, yeah, I will talk with Hall to make sure that the supporting materials.
Okay. I think that's all for logistics. I don't know, Mingwai or Danny, if you wanted to do any other general introductions for ACPC or anything.
So, Danny, do you want to do it too? Do you want to make some comments? Remarks?
Go ahead, Mingwai.
Okay. So I think, yeah, I think I would like to welcome everyone to the ACPC annual meeting. So this is the second time we do the virtual meeting, and many thanks to Andrew, to Matt for organizing the shadow session, and also I'm not sure whether Jiwon and others are here, to Mike, Jason, Jiwon Fa, and Scott Collis for their help organizing the deeper one. And I think special thanks went to Andrew and his colleagues at NCA for setting up the really nice the Zoom meeting, and also for a live stream for us. I think that's extremely helpful for us. So in the next 4 days, I think we are going to review and also to discuss what we have achieved in the past year. I think toward probably the roadmaps of the ACPC, and also some more general topics of the ACPC meetings. I think I checked the agenda, so we have about 60 long and short talks. So I thank all the speakers for because we have many talks. So I think in general the talks are short, and some are extremely short, like 2 minutes. So on behalf of the organizing committee, I thank all the speakers for their efforts to accommodate these pretty short talks. I understand it can be challenging for a lot of our speakers, and in fact for us, for our organizers too. So we will see. I think probably that's all I want to say. To thank you, Andrew. So Daniel, do you want to make further some comments too?
No, just join the welcome, and encourage the people, especially from the short talks, to upload more materials, and please provide the link to view that, so that we can view it if someone is interested, and in a timely manner, so we can involve that information also in the discussion.
Okay, good.
So let's the presentations begin.
So Andrew, yeah, your turn.
Okay.
So Simon, should you start the recording? Do you already start?
Sorry.
Or? Okay.
I can do it.
Yes. Okay, good. Yeah, I see it.
Whoop. Oh, that didn't do it. There. That's what I needed to do. Okay. Sorry about that.
So we will do the screen, the shot for during the discussion stage, right? Or should we do now?
No, we should do, if we're going to do screenshots or pictures, we should do them during the discussion. There'll probably be more people as more people come on. So
yeah.
Okay, so welcome everybody to the Shallow Cloud session. This is going to be the next 2 days, and Matt and I have sort of organized everything into a couple of different breaking things up. So the first section today will be on talking about cloud morphology and warm rain. We'll then move on to talk specifically talking about aerosols. And then tomorrow we'll switch gears a little bit, and we'll spend some time talking about sort of natural laboratories, which is a subject that we've been doing quite a bit of work on in the last year in the Shallow Cloud group. And then we'll talk about, there'll be some talks on COVID-related topics, and then on long-term trends. And for each of those 4 sessions, we're going to have 20 to 30 minutes of discussion. And we've got some really very interesting talks. Matt, did you want to add anything?
Nope, that sounds good to me.
Okay, so we'll just go in order. Dan's going to advance the slides. Just ask him to go to the next slide. And let's see, we have to go find people to actually mute them. unmute them. So first talk is Jingying Chen. There we are. So I can ask to unmute. You'll have to unmute yourself. There we go. And take it away. I'll try to give you a verbal warning at about something like 6 minutes, at about 4 or 5 minutes, when there's about 2 minutes to go.
Okay, can you hear me?
Yes.
Good. Hello, everyone. I am Jingyi Chen from Pacific Northwest National Lab. I'm going to talk about the factors controlling the mesoscale morphology and the evolution of shallow clouds. This work is supported by NASA project Aerosol Cloud Meteorology Interactions over the Western Atlantic experiments. I also would like to thank my co-authors, Hailong Wang and Xiang Yuli, for their contribution to this work. Next slide, please. The cloud streets are usually observed in many satellite images and aircraft measurements. The left figure showing here shows the structure of the cloud streets by the reflectivity along with the wind speed anomalies observed from an aircraft. The most commonly view of cloud streets is that they are a manifestation of convective organization by wind shear over the hot surface. However, how does the surface heating influence the characteristics of cloud streets along with the wind shear is still not clear. In this study, I'm going to show a cloud street case associated with cold air outbreak over the Western North Atlantic. The right figure shows the albedo from the GOES-16, illustrating the dissipation of the post-frontal clouds with the specific structures. I'm going to focus on the scientific question, that is, what are the factors associated with the characteristics of those cloud streets? Next slide, please. Thanks. We use nested warp simulations. Here I show snapshots of the total water paths, including both liquid and all ice phase at the 10 o'clock Eastern time for the North Atlantic region. The top left figure shows the outer domain with the 3 kilometer grid spacing, and the inner domain is shown in the bottom left with 1 kilometer grid spacing. The right column shows the liquid water path or ice water path from the satellite from the GOES-16 2 kilometer dataset. The simulated post-frontal cloud structure is generally consistent with the GOES-16 in the observation. The large scale forcing of this example is from Erf5 reanalysis dataset. Next slide, please. Thanks. We have tested the simulated cloud structure with different large scale forcing. The top row is based on the FNL analysis dataset, while the bottom row is based on the Erf5 reanalysis dataset. The simulated cloud structure shows evident differences that the simulations with the Erf5 shows larger values of the total water path in the inner domain. One of the differences in the large-scale forcing is surface forcing. The simulated surface fluxes are shown in the right two figures. Erf5 reanalysis considers the satellite data and shows larger values and gradients in the sea surface fluxes. Thus, it suggested that the boundary layer development in the local morning slowed down the post-frontal cloud dissipation. The surface forcing from Erf5 shows stronger fluxes and slow down the dissipation comparing with FNL. Next slide, please. Thanks. To validate the results that the differences of the surface forcing from Erf5 and FNL leads to the differences in the simulated cloud field, we swap the surface properties of the large-scale forcing to another simulation. The variable determining the surface forcing from the large-scale dataset is the sea surface temperature, SST. The top left figures show SST in early morning, and the two right figures shows the differences between the two forcing datasets. Erf5 shows larger spatial gradient in SST in the inner domain. Bottom figure shows the time series of the total water path. blue lines is based on ERA5 and the orange lines are based on the FNL. Dashed lines are the simulations with the swapped sea surface temperature. When the SST in FNL is changed to the one from the ERA5, total water pass is increased. When the SST in the ERA5 is changed to the ones from FNL, the total water pass is decreased. Thus, we can conclude that the sea surface temperature from ERA5 leads to a higher total water pass in this case study. Next slide, please. Thanks. Furthermore, we examined the cloud size distribution from those 4 simulations. Left 2 figures give an example about the cloud objects we identified by the total water pass field. Middle 4 figures shows the time series of the cloud size distribution from the 2 simulations with ERA5 and FNL showing on the top, and the swapped SST2 simulations showing in the bottom. The decrease of the peak cloud size can be seen in all the 4 simulations, indicating the dissipation of this period. Right 4 figures shows the cloud size distribution at 3 times in the morning, 9, 11, and 13 Eastern time. At 9 Eastern time, the simulations with SST from ERA5 has a smaller peak cloud size, and those with SST from FNL has a larger peak cloud size, indicating that the sea surface temperature from ERA5 favors cloud broken in the early morning before 9 o'clock EST. At 13 EST, the peak cloud size are similar for all the 4 simulations. Those results suggest that the sea surface temperature and the surface fluxes have an impact on the evolution of cloud size distribution. Next slide, please. Here is the.
Oh, there we go. Yep. Go ahead.
Okay.
Sorry.
Yeah. Yeah. This is the last slide, and the simulated post-frontal cloud structure is generally consistent with the observation from the GO16. And also we see the post-frontal clouds are sensitive to the choice of forcing data set. We show that the surface heating impact the cloud water amount and the cloud size evolution during the daytime. And in the future work, we will continue to examine the wind shear and the aerosols to see their impacts on the characteristics of the cloud street. That's all I have today. Thank you. And if you have any questions, yeah, feel free to send me email or post it in the chat.
Thank you, Jingyi. I guess I'll ask a quick question. So what are you actually using right now for aerosols in the WRF simulations?
So far, we use the Morrison's scheme, and the number concentration of the droplet are prescribed with a values that based on the observation field from the measurements. The value is close to the 450 per cubic centimeters, and we don't have more explicit represent about the aerosols so far.
Okay, thank you.
Thanks.
Let's see, one quick question from Mingwei. Are the results sensitive to resolution, do you think?
Oh, yes. This for the current simulations for the inner domain, we use 1 kilometer and the outer domain for the 3 kilometers. We don't have the convective scheme, and we open the PBL scheme. We have tried the simulations with the coarser resolutions like 3 kilometers and 9 kilometers. The liquid water path is generally evidently smaller than those ones from the observations, and also smaller than those ones with the higher resolution simulation. Yeah.
Okay, thank you. And Jan, I see you're there. We'll let you take it away.
Thank you. To motivate this study, I am showing here profiles of the vertical pressure velocity at 4 locations. And these were taken by radiosondes that were dropped from aircraft. What I want you to notice is the structure in these profiles, which indicates upward and downward motion. And to give you an idea of the magnitude, 5 hectopascals per hour corresponds to roughly 15 millimeters per second. The question that I want to explore and answer in this presentation is, does this structure matter and what are its consequences? Next slide, please. To answer this question, I used Lagrangian large eddy simulations, which track the evolution of a stratocumulus cloud field off the coast of southwestern Africa. In panel A and B, you see satellite snapshots of this stratocumulus cloud field overlaid with the locations of 3 simulation domains drawn to scale, which track the evolution of the cloud deck. What you see is in the small pictures, that's the cloud field inside these simulations. What's happening here is a transition from an overcast closed cell cloud state into a broken open cell cloud state. And in fact, a pocket of open cells forms, and you can see that in panel B. On the right-hand side, you see the evaluation of these simulations against satellite retrievals. And the take-home point here is that both in terms of cloud optical depth and cloud effective radius, these simulations show a really good agreement relative to the satellite data. Next slide, please. Now, these simulations are driven by the Erf5 Meteorology, which also provides the subsidence along these trajectories. And in this slide, I'm focusing on the green trajectory. In panel A, you see the time height curtain of subsidence provided by Erf5. The red hues denote upward motion, the blue hues downward motion. The arrow points to one instance of upward motion in the boundary layer, and you can see several of those. And this is what we want to explore in this presentation. Now, in panel B, you see a different version of this subsidence field. Here, I have vertically homogenized it 12 hours into the simulation between the surface and 4 kilometers. And the arrow points to that location where previously there has been this event of upward motion, which is no longer there. On the right-hand side, you see the time series from these simulations. The light green, that's the simulation with the original subsidence field. The dark green, that's the simulation with the homogenized subsidence field. The first thing that we notice is that the homogenization leads to a lower inversion height shown in panel C. This lower inversion leads to a reduced liquid water path, a slower buildup of rainwater, and a delay in surface precipitation, which is shown in panel D and indicated by the arrow. The delay is about 12 hours. This delay in precipitation is accompanied by a transition between the closed and open cells that is delayed by about 12 hours as well. We diagnose that here by the cloud fraction, which is shown in panel E. Again, the delay is about 12 hours. Next slide, please. Now, if we compare these two simulations against the satellite data, we first of all see this really good agreement between the original simulation and the satellite retrievals. The simulation with the homogenized subsidence field, in contrast, disagrees quite significantly relative to the satellite data. We also see a disagreement in this simulation relative to in situ observations. These were taken during the Flight 52 of the Clarify field campaign. Here we see this reduced inversion height, which indicates again this disagreement relative to the observations. Next slide, please. Now, we can ask the question, is there perhaps some free parameter in these simulations that we can use to actually tune the simulation with the homogenized subsidence field to restore the agreement with the observations? And in fact, there is such a free parameter, and there's only one free parameter that we can tune, and that's the initial aerosol concentration. Here I'm showing a third simulation, which is denoted by the yellow curves, and this one was initialized with a reduced aerosol concentration that's shown in panel A. This reduction in aerosol leads to an earlier onset in precipitation. This is shown in panel B and indicated by the arrow relative to the dark green simulation. However, we also see, and that's shown in panel C, that the inversion is further lowered away from the original simulation. Now, if we compare this new simulation with the satellite data, and that's shown in panel D and E, we see that indeed we were able to restore this agreement with the satellite observations. But if we move on to the in situ data shown in panel F and G, here we see that this lowered inversion height actually results in a stronger disagreement relative to the in situ data. So here the point is that we were unable to tune this simulation by using the only available free parameter to restore agreement with the observations when we homogenize the subsidence field. And this brings me to the conclusions on my final slide. So what we've shown here is that the vertical structure in lower tropospheric subsidence matters and is important for the evolution of stratocumulus clouds. It co-determines the timing of precipitation, and in this specific case, it co-determines the timing of the transition from a closed cell to an open cell state and the timing of the formation of a pocket of open cells. We've also shown that temporally and vertically quite limited features in subsidence can in fact initiate the formation of such a pocket of open cells, and such limited features can in fact be caused by gravity waves. And my final conclusion, and I find this particularly interesting, is that Erf5 seems to capture the vertical structure in subsidence that is necessary to reproduce observations when driving a large eddy simulations with the Erf5 meteorology. When we remove this vertical structure in subsidence by homogenizing it, we're no longer able to reproduce the observations even by tuning the remaining available free parameter in the simulations, which is initial aerosol concentration. And that's it for me, from me for today. Thank you.
Thanks, Jan. Question in the chat: is the difference because of the subsidence structure or just the subsidence at the inversion top?
Yeah, that's an interesting question, and I think it really is, in fact, is these events of upward motion inside the boundary layer that lift the inversion. You have to really move the entire boundary layer up in order to create a higher inversion. It is not sufficient to just have a stronger upward motion at the inversion.
And one more question. Let's see. Actually, there's a couple of questions. I think I'll let you answer them in the chat from Bakita and from Danny about the inversion, and we'll go on to the next talk, which is Jiquang Dong, which, let me see, unmute. There you go. Okay.
Hello, everybody. My name is Xiquan Dong. This is our talk. And this talk mainly based on the two papers from my former student Peng Wu in GGR, and also it's my paper JRL. As we know, it's most climate model predict too frequently and too light precipitation. So in this study, we want to use the newly retrieved the marine boundary cloud and drizzle property to modify the KK 2000 auto conversion and accretion rate. And the run is we apply the updated scheme to the UNCAR CS1 model next. As we know, it's a great challenge to retrieve marine boundary cloud and the drizzle microphysical property simultaneously. So it's our first step actually is to decompose the cloud to drizzle reflectivity from the Kaiser measurement. And what we are doing is we're using the aircraft measures cloud property to categorize radar effectivity, the red color here, and using the 2DS measure drizzle property to categorize their reflectivity. We found is a minus 15 dBz is almost the maximum for cloud is a particle size is a contribution. So in the cloud is a 0 and the cloud base, and 1 is a cloud top, and where is the fund height is a minus 15 dBz, and that's above is contributed by cloud, below is contributed by both cloud and drizzle. And below the cloud base is 0 is here is only contributed by drizzle. So we found is the difference is drizzle, right? So we get the red line is a cloud radar activity, and it's a blue is a drizzle. So we developed some algorithm to retrieve the cloud property next. And here is a sample is over retrieval, and you can see the cloud radar effectivity, and right part is a drizzle property. You can see cloud is basically follow adiabatic increase from cloud base to the top, and the increase is from cloud base to top. And the drizzle property on the right side is basically it's a larger, it's a particle size increase from top to the base, opposite to cloud, and the number concentration is highest near the cloud top, and its liquid content is maximum near the center next. Well, after we do the retrieval, we also compare the aircraft in situ measurement. The red color is line is a retrieval. The blue is from the aircraft, and you can see the left side is a time series, and as you can see, the first column is cloud property, the second column is for the drizzle property. That's a change with time. And what is the right part is for vertical distribution, is you can say basically cloud is increased from cloud top to from cloud base to the top for particle size and liquid content, and number concentration almost constant. However, for the drizzle, is increased from top to the base. And also you can say it's from both time series and vertical profile. Good agreement is between retrieval and error spatial measurement. Next. Well, after we got here, so we want to, how to use this retrieval to modify, is improved, is auto convergent accuracy rate. Is the light part is from KK 2000, and A and B are constant, as we know. And in our study, we are modified A prime, B prime in right side. And you say this is not constant anymore, it's a function of the height, and also is a function of cloud is particle size, and also is a drizzle particle size. Next. Well, this is what we got here, and this is from cloud base is 0 and the top is this what is relative contribution normalized. The right solid line is represent original KK. Emergent is the new one is a dash line. Is the red color represent auto convergent, is a blue red accuracy. And what it will say near the cloud top, KK is auto convergent accuracy contribute about 45 and 55 of total drizzle equal content. Well, our new one is R prime, the dash line is a contribute about 31 and 61. That means 40% less is, and also 40% more in the auto convergent accuracy from the original one. The new KK scheme is a lower drizzle frequency and higher drizzle intensity than the original KK scheme. That is the support is we already found is a KK scheme overestimate auto convergent and underestimate accuracy rate, which could be reason for most of the GCM predict is too frequent and too light precipitation. Next.
2 minutes.
Okay. To review the relatively important, we also changes do the scientific study. You can see the A is what we show the liquid water pass using the new one minus old the KK region. We can say that is a new one is increased about 20%, and also the frequency, precipitation frequency decreased 10%. That's mainly due to the 40% less auto convergent rate near the cloud top. And also is the mean frequency drizzle or light precipitation was reduced from 25% to the 23% is globally. Last slide. Next. And also we compare our new when we improve this new scheme into the Anchor model, is we can see the new result simulate is a liquid path almost the same as the modest retrieval, although there is some little bit different. And also is the cloud relief forcing is they are also similar, is difference only is 2 watts. And because you can see the liquid water short wave forcing has a strong negative correlation with the cloud liquid path. That's it. Thank you.
Thank you. That was very interesting. Question from Ming Wai. How does the new KK reduce drizzle rate compared to the old KK scheme?
Okay, well, that's we showed the last slide is a drizzle frequency is reduced, but the drizzle intensity increase because you can say liquid path is increase, but the drizzle frequency decrease is because it's auto convergent rate at the top is a decrease 14%. That's the for frequency. Accuracy is the increase of 14% at cloud top. That's our conclusion is at the cloud top is mainly determined is a drizzle frequency and also intensity.
And is that because, so how do you get the changes at cloud top, or you put that's just because of the size distributions?
Yeah, it's based on the over retrieval. We can retrieve vertical profile from cloud base to the top. It's based on always a radar retrieval.
Okay. All right, very interesting. Thank you.
You're welcome.
Next talk is by Kenta Suzuki.
Hello, can you hear me?
Yes, we can. Go ahead, Kenta.
Okay. Good evening, everyone. I'm talking from
Yes,
Japan.
thanks for staying up so late.
Yes. So today I'd like to share some early results from GUX process evaluation study for warm rain. I'd like to acknowledge my co-authors and contributors from different institutes for different models. So next, please. So the GUX PROS WR is the a branch of the process evaluation study that's ongoing under the umbrella of GUX. And that's intended to do a process-oriented model diagnostics focused on the warm rain process, where some metrics or diagnostics are intended to be developed to observationally probe the warm rain process. And particularly through application of the satellite simulators to global models to construct some particular statistics that look at the warm rain processes that's directly comparable to satellite measurements. And in some models, alternating parameterizations are also tested to see kind of a sensitivity of the warm rain characteristics to different parameterizations. And showing in the right bottom is the just a list of models and contributors that's now currently participating to this intercomparison. Okay, so next, please. And we are looking at the basically the radar reflectivity at W band that's obtained from the cloud set observations. And showing in the left is the PDF of the radar reflectivity showing black from the observations and in different colors from different models, including different parameterizations. And overall, very interesting feature here is the kind of a bimodal characteristics as a model ensemble. That's a little bit different from the H-rain observation. That's more like a continuous distribution of the radar reflectivity. And according to this radar reflectivity, we can also define some different precipitation categories like cloud and drizzle and rain, according to some threshold of the radar reflectivity. And shown to the right is the fractional occurrences of these three different precipitation categories from observations and the different models. And probably you can find that there are pretty much diversity among the models in this cloud drizzle rain compositions. And some models are more closer to observations, but other models are deviate from the observations. So so this is one of the things we are now looking at. Okay, so can you go next? And for more a little bit detailed investigations, we are also looking at the geographical characteristics of the fractional occurrences of different rain categories. And shown here is the example for basically a non-precipitating cloud that's designated by condensation here. That's defined as the fractional occurrences of the non-precipitating cloud relative to all the warm rain, or the warm clouds. That's showing the upper panels. And also showing here is the early coalescence regime that's defined as the fractional occurrences of drizzle relative to drizzle plus rain. So that's a little bit closer looking at the coalescence processes. And also you can see that there are diversity in both the rain categories among the models, but the condensation, for example, tends to be separated into underestimated or overestimated depending on the models. And then the early coalescence also has overestimated and underestimating, but the in some subgroup of the model, for example, MIROC6, NICAM, and GFDL, for example, some geographical similarities can be found with differing magnitudes of the fractional occurrences of early coalescence. So that might suggest some kind of environmental control on the cloud microphysics, but the differing responses of microphysics to the environmental conditions. So this is kind of a second thing that we are now looking at. So can you go next? And the third thing we are looking at is the vertical dimension.
2 minutes.
Thank you. Vertical dimension of information. For example, in the form of the radar PDF of the radar reflectivity as a function of in-cloud optical depth that's further classified according to different cloud particle size. And showing in the left top is the H-line observation that shows the kind of a monotonic transition from the non-precipitating clouds to more like precipitating clouds as a fairly monotonic function of the cloud particle size. And models tends to be again separated into the more like precipitating, always precipitating type of models, and then there are also the always non-precipitating type of clouds. So this is probably another very interesting thing that probably says something about the microphysical process characteristics. And we are also now looking at the kind of sensitivity of this type of statistics to the differing parameterizations in a given model. But here's just a model ensemble results just for overview of the model ensemble results that's analyzed here. Okay, so can you go next? Okay, so in summary, initial analysis from the GVX Pro's warm rain has been conducted with some of the latest generation global models, including the global cloud resolving NICAM, actually. And yeah, so I forgot mentioning, but the one interesting feature is the model biases of the precipitation, warm rain precipitation is also shared by the global cloud resolving model NICAM. So that's more like highlighting the kind of an issue in the cloud microphysics parameterization rather than horizontal resolutions. And then simulated cloud precipitation observables are jointly analyzed to investigate global characteristics of the warm rain process to find some interesting features. And we are still in the early phase of analysis, actually. So if you are interested in some aspects of this analysis, you are definitely welcome to join. So yeah, thank you very much. This is all I have today. Thank you,
Kenta. One quick question from Ming-Wai. How do you separate the condensation from the early precipitation?
Oh yeah, that's very simply by the threshold of radar reflectivity here. So radar reflectivity of -15 dBz for the column maximum radar reflectivity, actually. Yeah. Does it answer the question?
Yes, I think it does. So, okay. Thanks very much, Kenta. And now we're moving on to the last of the longer talk. So this is by Ping Ping. I think, let's see, we get you unmuted there.
Good morning from,
yeah, oh, there we go.
Colorado. Okay, so you can hear me well. Well,
yes.
First of all, thank you, the organizers and everybody who is here this morning. So yeah, next slide, please. So this work is a modeling aspect of the Atomic Field Campaign, which is a joint campaign with the Eureka. And it took place in 2020, between January and February, over the eastern part of Barbados. So in this work, we use a Lagrangian large Eddy simulation following a trajectory based on Erf5 data to try to represent an event of transition between sugar clouds to flowers clouds in the Atlantic. So quick terminology, flowers clouds are shallow cumulus that are very shallow and occur at very fine scales, whereas the flowers clouds are slightly deeper, and from the satellite image, they can have the appearance similar to closed-cell stratocumulus, but they're still shallow cumulus, and they also have well-defined stratiform cloudiness in the shallow cumulus part itself. So the trajectory here is represented by the yellow dots, and they follow the air mass at 500-meter altitude. They also pass through the research ship called the Ron Brown from NOAA's observation, and that's marked by the pink cross at the center of the satellite image. Next slide, please. And so here we're trying to understand, try to simulate the transition and understand a key mechanism for this transition. So we use the system for atmospheric modeling for this work. And here we have two simulations, the control run that follows or uses all the large scale forcings from Erf5 data. In addition, we tweak one parameter, and that is the large scale vertical velocity between 10 and 20 UTC. This second simulation is called weaker W. So this time that we reduce the vertical velocity is during the transition from the sugar clouds to the flowers clouds. Next slide, please. And here I'm showing you the results from the control simulation. The top left panels are the snapshots from SAM simulation. And you can see that the cloud clusters grow with time. Toward the end, the shallow cumulus clouds are larger and they precipitate slightly, so they also produce a little bit of cold pools. The bottom left panel shows the domain mean time height curtain. The colors represent the domain mean vertical velocity, and the two lines, solid and dashed lines, are the cloud top and cloud base heights. We also see clearly that there is a deepening of the cloud layer, especially as the domain mean vertical velocity is positive, and that affects the cloud top height. Top right is a comparison between SAM domain mean profiles and the observation from the Ron Brown at the same period and the same time. And our control simulation is consistent with the observation well. Next slide, please. So here we show the profiles of cloud fraction at the top and vertical velocity at the bottom. For the top panel, the left part is the domain mean and the right part is cloud fraction sorted by total water path. Q4 or quartile 4 represents the moistest areas of the domain. And at this time, this is the early state of the aggregation process. So the flowers clouds are not the largest that we have in the simulation, but we picked this time because it's when the domain mean vertical velocity in the control simulation is positive and also larger than the weak W simulation. So we can directly compare the effect of vertical velocity. And in the bottom right panel, we show the perturbation of vertical velocity at the mesoscale. The darkest blue line represents the moistest region where we have local ascending air in the cloud. And so there is a mesoscale circulation of between the dry and moist regions. There is net convergence of moisture into the moist layer or the moist columns, making the moist areas moister and dry areas drier. This also increased the total water variance in the simulation. Next slide, please.
2 minutes.
Okay, thanks. So one thing I forgot to mention in the previous slide is that with stronger large domain vertical velocity, there is also stronger mesoscale circulation in the control simulation compared to weak W. So here we compare the buoyant total kinetic energy production between these two simulations at all scale as well. So there, as time goes on, there is an increase in TKE production at the mesoscale, shown by the top panel. The bottom is the ratio between the control and weak W simulation. The ratio that's more than 1 means that the TKE production in the control run is larger, and that's the case here. So what I'm not showing here is that we also compute the same spectra of QT variance, and because it's hard to just look at the change from one simulation, we look at the ratio, which is a relative increase of TKE production and QT variance between control and weak W. And it suggests that the increase in TKE production in control run precedes that from QT variance. So the boost in large scale vertical velocity favors TKE production at the mesoscale, which drives the moisture aggregation. Next slide, please. And that's final slide, conclusion. So we have used Lagrangian large eddy simulation to reproduce a transition of shallow cumulus from sugar to flowers during the atomic and eureka field campaign. And while large-scale outward vertical velocity deepens the cloud layer, mesoscale wind makes the moist areas moister and dry areas drier, assisting the cloud organization. Stronger large-scale vertical motion strengthens the mesoscale circulation, and that helps accelerate the transition process. And in the future, we'll examine the role of cold pools as well as the cloud aerosol interactions with this work. Thank you.
Thanks, Ping Ping. I had a question. So you talked about the increase in vertical velocity. Is that over a whole depth, or does like shear matter to this of the vertical velocity? Have you looked at that at all?
Oh yeah, that's a good point. And we haven't looked at the shear yet. So we look at the strength of vertical velocity at the whole depth from the bottom to the top. It's of interest to us to look at the structure and the shear in more details in the future too. Thank you.
Okay, thank you. I think, Ping Ping, there's another question in the chat also, which you can pick up. Okay. Now we are going to try something a little bit different. This will be entertaining. So now we're going to switch over to doing 2-minute research highlights. So these are really quick. We're going to let everybody go and try to stay on time. We'll try to encourage you. We have 5 or 6 talks. Sendip, I think, is not online, and we're going to do his because he had something else to do this today. So this time didn't quite work for him at the last minute. We're going to move that to the second session today, and hopefully we'll be back by then. So I'll try to go through as people are talking. We'll hold all our questions, I think, to the end on this, and as we then get into the discussion. So Xiaoli, why don't you take it away, and I'll try to unmute everybody else faster than you can start. So go ahead. Here, Xiaoli, I'm asking you to unmute again. Hopefully you can, there we go.
Okay, so can you hear me?
Yes, we can.
Okay, great. So this is a recent study in collaboration with Jianhao Zhang and Graham Fungo, and we basically look at the environmental control on the brightness of marine clouds over the North Atlantic Ocean, and we found a strong control of the sea surface temperature. Our study focused on a domain of 30 degree by 35 degree over North Atlantic, and we combine the satellite measurements and Erf5 reanalysis data. If you look at the right 2 panels, where I show you the bin average cloud albedo susceptibility on the left and SST on the right with respect to the relative humidity at 800 hectopascal and estimated inversion strength, you can see clearly the similarity between these 2 panels that indicates SST can well modulate the lower tropospheric stability and free tropospheric relative humidity, and therefore have a control on the brightness of marine clouds. Next slide, please. So on the left, I'm showing you the bin average cloud albedo susceptibility on the SST and EIS domain, and you can see the high local SST favors the cloud darkening. And we think that that is attributed to 2 typical scenarios. Scenario number 1, is when there is only increase in local SST, this will deepen the cloud boundary layer height by reducing the EIS, which corresponds to the diagonal direction on the SST and the EIS domain shown in the middle. So the deepening boundary layer height would directly reduce the absolute humidity above the cloud layer, which facilitates the cloud top entrainment drying. Scenario number 2 is when there is an increase in SST both locally and remotely. This will keep the inversion strength relatively unchanged, but the relative humidity in the free troposphere reduced a lot due to the increase of the temperature, and that corresponds to the horizontal direction on the SST and EIS domain. So in a nutshell, we anticipate a more frequent occurrence of less reflective clouds, that is a warming effect over the North Atlantic with global warming or with the strengthening phase of the Atlantic meridional overturning circulation. Thank you.
Thank you. Let's move on to Sheng Yu.
Hello, everyone. Today I'm going to present the large eddy simulations of marine boundary layer clouds observed during the ACTIVATE campaign. The ACTIVATE stands for the Aerosol Cloud Meteorology Interactions over the Western Atlantic experiment. Next one, please. 2 cold air outbreak events were observed during the ACTIVATE campaign, one on the 28th of February 2020, and another one is on the 1st of March 2020. They're all off the coast of Hampton, Virginia. As you can see that the sea surface temperature are very different for these 2 events. Therefore, the meteorological and large-scale ambient conditions are very different. So we're going to study how this difference contributes to the evolution and the formation of the clouds. So here we're first constructing the large-scale forcing by comparing the Erf5 root analysis and drop sounds measurements. We see generally good agreement between the Erf5 root analysis and the drop sounds measurements. And we also see very strong temporal and spatial variations for both cases. So there we use the constructed and constrained large-scale divergence surface heat fluxes and the tendencies of theta and QV and horizontal wind speeds to drive the large-scale simulation. They're all from the hourly Erf5 root analysis. And we show that the agreement between the large eddy simulation, drop sounds measurements, and Erf5 root analysis are pretty good. And also we observe a very fast evolving boundary layer for these 2 cold air outbreak events. And so we conclude that the large-scale thermodynamic advective tendencies and the wind relaxations are really important to drive the large eddy simulation and to capture the observed fast-evolving boundary layer meteorology states, and particularly the divergence is very important for the large eddy simulation. Thank you.
Thank you, Sheng Yu, sorry. Rachel, you're next.
Hello. Yeah, so I've been emulating the relationship between the inversion jumps of potential temperature and total water mass mixing ratio and the cloud liquid water pass. So you can see the response surface here that represents that relationship, where the faint markers are the training data for the emulator, from where we've perturbed these vertical profiles for those 2 parameters from a uniform stratocumulus LAS model. And you can see it's a smooth function over the parameter space, but there are some bumps in it, and that's from the randomness in the LAS model, which represents the cloud's natural variability. Next slide, please. So we can use a nugget term when we build the emulator to define that variability. So normally without a nugget term, the emulator interpolates exactly through the training data, and that's where you get this bumpiness from. But then each of these training data points are actually just sampling the distribution of possible model outputs from that depends on those initial conditions. So when we kind of quantify that distribution and build that into our emulator, we get a smoother response surface, which is actually more representative of that general behavior and not specific to individual simulations. Next slide, please. So here I'm showing a comparison of a few different nugget terms, from no nugget term in the left column here up to quite a large nugget term in the right column. And we find that when it's derived from model simulations, then it is the best representation. So the histograms here are sampled from those kind of distributions I showed on the slide before. And we find that they agree best by the Kolmogorov-Smirnov p-value test when it is taken from ensembles run at the training data points. So in this way, we can get a better idea of the general behavior of the cloud. Thanks.
Great, thank you. Next is Yutong.
Can you hear me?
Yes, we can.
Okay, so I'm talking about the role of the surface latent heat fluxes in shallow cloud transitions from the perspective of theory and LES. Next slide, please. And we all know that the surface latent heat flux has been considered as the dominant driver of the stratocumulus transitions in subtropical eastern oceans. We have a very well-known theory proposed by Breston and Wyand, who argues that increase in the latent heat fluxes, it drives everything here. Next slide, please. But however, the observations suggest otherwise. This is the ship-based observations from the Magic Field campaign from California to Hawaii. So you can see that the surface latent heat flux does not change that much along the climatological trajectory of the cloud regime transitions off the west coast of California. And this motivates us to ask a question. Next slide, please. How determinant is the latent heat fluxes to the cloud regime transitions? And we address this question from two perspectives. And the first perspective is from the theory. And the key conclusion from the theoretical perspective is that we found the temperature inversion near the cloud top is crucially important for the decoupling to happen. So if the inversion is weaker than usual, the entrainment will be very efficient, which can promote the warming of the cloud layers and thereby decoupling. And to test this hypothesis, we ran a large simulations using the same model for the Aztecs field campaign. And then we conduct a mechanism deny experiment for which we does not allow the latent heat fluxes to increase with the SST. Next slide, please. So here are two key take-home messages here. The first is that the increase in the latent heat flux is not necessarily needed for the decoupling. Okay, so if the temperature inversion is weaker than usual, the entrainment is very efficient, which can promote the decoupling by enhancing the warming of the cloud layers. But the latent heat flux is still very important for the cloud regime to happen. Okay, so if you want to know the detail of these studies, you can click on this link, which has been submitted to JS. Yeah, that's it. Thank you.
Thank you. Next up is Jake. Go ahead.
Okay, hello everyone. My name is Jake Gristy from Ceres and NOAA. And together with my colleagues listed in the top right, we've been looking at understanding and predicting surface solar irradiance variability beneath shallow cumulus clouds. As what's shown on this slide are probability density functions of the downwelling surface solar irradiance. So on the left are observations for one particular example. We see this typical bimodal PDF where we have a mode at smaller radiance associated with the cloud shadows and a mode at larger radiance associated with the clear sky between. Now, our large Eddy simulation for this case is shown on the right. You see, with typical 1D radiation calculations, we get the orange PDF where we don't capture this, represent the observations very well at all. But if we take the same cloud field from the large Eddy simulation and plug it into a 3D radiative transfer simulator, we get the PDF in blue, which provides a much better representation of the observations and highlights the importance of 3D cloud radiative effects within these conditions. So next slide, please. So one of the issues with these 3D radiation calculations is that they're extremely expensive. So one of the things that we've been looking at is how well can we predict these surface irradiance PDFs using just a handful of cloud fill properties. So those are given in the bottom right, things like the cloud fraction, the sizes of the clouds and the distances between them. And the three plots at the top are showing in the orange, the truth PDF, and then in the black and the green dash predictions by 2 machine learning algorithms. And what we see is that these algorithms are accurately predicting variations in the shape and size of both of these modes, and therefore providing a much better representation than the 1D radiation calculations I showed on the previous slide. Current work is extending this not only to the cloud properties, but also to the aerosol properties. The plot at the bottom shows why this is important. The blue line shows cloud-only simulations, the black cloud plus aerosol. You see that the inclusion of the aerosol can perturb both of these modes in the distribution. So look out for that work coming soon. Thanks.
Great, thank you. And last but not least is James. I think I got you unmuted.
Hello?
There we go.
Yeah.
Yep.
Next slide. Next slide. High resolution extended supersaturation range CCN spectra often show variations from bimodal to unimodal. You went back one slide. Unimodal is usually only the Aitken mode. Bimodal includes got to go back one slide. Anyway. Yeah, we quantify the CCN modality by the concentration difference between the two modes and divide by the sum to get the normalized difference, NDF. A lower NDF indicates bimodality. Next slide, in the MACE stratus clouds, we find more drizzle when the CCN spectrum is unimodal than when it's bimodal. And in the ice-T cumulus clouds, the opposite, more drizzle when it's CCN or bimodal. And the same is now being found in the RICO cumulus clouds. More drizzle when the CCN spectrum is bimodal rather than unimodal. The next slide shows quantifying the difference between the bimodal and unimodal CCN for drizzle. And this shows more drizzle for bimodal, regardless of the liquid water content used to define the clouds. So there you can see some differences there. Greater drizzle differences happen at higher altitudes where there's more drizzle, and that's what I'm showing here. I don't have time to show you other altitudes. At the highest altitude range shown here, there's an order of magnitude more drizzle for bimodal CCN rather than unimodal CCN. This is seen for all 4 probes, the FSSB for the large cloud droplets and the 3 probes for drizzle, all showing similar differences. Quite a big difference between bimodal and unimodal CCN, that's all.
Great. Thank you. Okay, well, we actually got through that and reasonably on time. Thanks to all the speakers for doing that. And now we're going to have, for the rest of this half hour at least, that will launch into some discussion. And Matt, you want to take it away from here. So if you have comments, please raise your hand. We can make sure then we unmute you. The co-host can watch or Matt or I guess Matt can call on people, or I'll help monitor also the people in the who raise their hand. The raise hand function is under reactions. If you go to reactions and then on the bottom of your Zoom screen, and then it's raise hand. Okay, take it away, Matt.
Thanks, Andrew. So that was a great set of talks from everyone, and it really quite clearly shows the strong links between, I think, cloud morphology and precipitation processes, radiation, and the fidelity of these models to be able to represent these structures is certainly getting better over time. I think now is a great time to open up the discussion. So if anyone would like to raise their hand, now is the time. And you can ask questions to any of the prior speakers, or raise new points too for the discussion. Oh,
Thumbs up from Danny. I raised my hand. I'll ask a question.
okay.
Yep.
Can you hear me, Matt? There's no one else. So I was.
I did.
Did you want to say something, Danny? Go ahead.
I did thumbs up, but I don't know why it is not showing.
There it is. Now it is.
I see it.
I see.
Now it's back.
Okay, so let me ask it. I was fascinated. Actually, we have here to get the discussion on track. Here we have the duality of the role of dynamics and heat flux versus the role of aerosols. I was fascinated by Jan Kazel, who showed the role of the divergence, and then I asked him whether the divergence might control the cloud base height. When there is more subsidence divergence, there is more drying and less liquid water pass, and then for the same aerosol, there would be, and same inversion height, there would be less liquid water pass and less drizzle. So first, I would like to ask Jan if he would concur with that idea, and I would like to encourage discussing the complementary or opposite roles of dynamics and aerosols.
Hi, Danny and everyone. Yes, I think I haven't actually looked at this. These simulations are really just fresh off the supercomputer, and so the analysis, we still have to do quite a bit of analysis, but I do agree with you. I think that changes in subsidence and in the subsidence structure, they really can change the cloud base height, and perhaps, and I suppose that from a physical point of view, I think it's very very reasonable to assume that they also could change the coupling state of the boundary layer by changing the amount of liquid water, by changing the cooling rate, the long wave cooling rate of the boundary layer and turbulence. So I think, yeah, I think you're right.
Thanks.
Graham Feingold is raising his hand.
Shiquan was first and then Graham.
Oh, okay.
I have a question for Ken about definition for the drizzle and the rain. Well, in our research study from the ground-based radar, we quite often found is a drizzle radar effectivity can more than 0 dBz. So my question is, how can you define or classify the difference between drizzle and the rain? Is it purely based on the radar effectivity or also based on some size, different size?
Sorry, that was to
Suzuki.
Oh, to Kenta. Let me see if Kenta's still muted. Sorry, Kenta.
Okay.
Go ahead.
Yeah, thank you. Yeah, so that's simply based on the radar reflectivity threshold that's obtained from the cloud set or models simulated reflectivity profile, looking at the maximum radar reflectivity in the column. And we have just defined the drizzle threshold like of -15 dBz and the rain threshold at 0 dBz. That's it, basically. So that probably influenced by the attenuation thing compared to the ground-based observation, I think. So that might be one source of uncertainty. That probably what you were kind of worried about. Yeah. But the definition is very simple in our analysis.
Great. Graham, would you like to go ahead?
Yes, I'd like to go back to the point that Danny raised. I came away from the session with exactly the same impression that we've got these meteorological controls over clouds and we've got aerosol controls. And his question, I think, went to the heart of the fact that we've got these strong couplings between aerosol and meteorology, and the cloud responds to both. And I think it sort of brings up this question of the extent to which we can really untangle aerosol effects from meteorological effects. And this notion, perhaps, that another way of thinking about it is to think more about the covariability of aerosol and meteorology. And I know I'm broadening the discussion here, because how does one define vertical structure in subsidence? It's not just the strength of the subsidence as a meteorological control, but also structure. So it becomes more complicated than that. But anyhow, I think, you know, as a discussion item, it's worth thinking about untangling these effects versus understanding their couplings and trying to see this in terms of a strongly coupled system.
So Graham, continuing on that theme and based on something that Jan was talking about, so what is the mechanism, do you think, of that coupling? I mean, Jan, so for example, mentioned cooling rates, turbulence, and changing liquid water path with aerosols. It would seem to me that cooling rates are slow unless they're evaporative, right? If it's a radiative cooling rate, but if an evaporative cooling rate would be fast enough to sort of couple those things, or I don't know, what do you think?
Well, the details of those simulations, I'll let Jan jump in. But you know, there's some examples over here. I think there was a question in the chat: why, why is the boundary layer shallower in the case of the lower aerosol? Well, in the case of lower aerosol, there was more drizzle, and so there was a suppression of the deepening of the boundary layer. Well, that lower boundary layer also came from the homogenized vertical velocity structure. And so in a natural situation where you're not looking at LES output, where you think you could try to untangle all of that, it's quite difficult to understand these responses unless you come at it with a whole series of these constrained simulations, constrained by Erf5, for example, and then do these, take these orthogonal directions in your simulations to try to tease that all out. So, these responses, yes, I like the idea of thinking about rapid responses versus slower timescale responses as a way perhaps of answering your question. But more specifically to these simulations, I'll let Jan weigh in.
Jan?
Yeah, so, sorry, go ahead.
Oh no, I was just going to ask you if you'd like to respond.
Yeah, so I think we're looking really at a very interesting kind of field of problems here. I mean, it's no longer just about the aerosol. We're looking at really complex questions. I mean, timing seems to matter a lot, and both timing in terms of the aerosol properties, but also in terms of dynamics. We've seen that relatively small changes in dynamics and in aerosol can send the boundary layer and the cloud properties on a different trajectory, different evolution. And I still have to wrap my mind around some of these questions, but I think this is really an interesting time to do this kind of research. And I know I'm being a little bit unspecific here with what I'm saying, so if there are any specific questions, I'm very happy to answer those. And I just wanted to express kind of my excitement about actually what we've learned and seen today in all the presentations.
Rob, would you like to?
Yeah, I mean, continuing on with this theme, I find it kind of disturbing that, these small, maybe not small, but they're sort of, I would describe them as quasi-random perturbations in subsidence, for example. Same could be true of stability, blobs of warm air, are driving kind of profound changes in the boundary layer. So in Jan's simulations, the subsidence change was only a small one, but it persisted for essentially the days afterwards, right? So on the other hand, I think it was Jiangyu Li's comparison between error subsidence and the activate dropsons didn't really show great correlation on those small scale blobs, right? So essentially they're unpredictable, which means that you know, they're not deterministic, right? So these profound changes are not predictable. So I don't know where to go from there, but it's just an observation. I'm not confident that we're going to be able to, that error is going to capture the time and place of those things. It might capture the PDF of them and the variability of these updrafts, but capturing the exact timing, I'm not confident.
Andrew?
But Rob, it seemed like the simulations were pretty able to capture the evolution. So is there something in the large scale that's reflected in these things that would be captured so that the subsidence, small scale subsidence is just an indicator of something else happening in the dynamics, either large scale convergence or divergence perhaps, and the vertical structure of that?
Well, I don't know. I would ask Jan to maybe talk about that, but we found many cases where you're not able to capture them, but if you do these little perturbations, you are. So it's like you can always tweak the model to get, well, you can't always tweak it, but sometimes you could. For example, how do we know that droplet concentration was the correct one to use? If you choose a different one, or if you choose a different drizzle scheme, you can probably get the model to agree. What I'm saying is that essentially, I'm not even sure we want to get the model to agree, because I don't think it should be able to agree in any one case, and maybe it's an ensemble. We should be doing ensembles.
It gets back to what Rob was talking about what Graham was talking about with mechanisms, right? Understanding actually what the mechanisms are. And then if you can do that, I'm thinking at it from a large scale modeling context, how do you then make sure that we can express these mechanisms at the bulk scale where we're not able to resolve all the processes?
Mm.
And I wonder to what extent too, the timings of the changes in cloud morphology might be related to gravity waves rippling through the boundary layer. And I don't know if people have looked at trying to simulate that in regional scale models to look at triggering mechanisms.
Matt, there was a study by a group from the UK, and I forget the lead author, Rob might remember, from vocals, looking at the role of gravity waves in the Southeast Pacific. Anything that will, I shouldn't say anything, but a gravity wave can deepen clouds and generate drizzle. And for example, opening of a park, low aerosol, of course, these subtleties of what's really driving what. And then the responses that occur as soon as you get that initiation of a thickening of the cloud. It's all quite subtle, and this is where I think these shallow boundary layer clouds are way more interesting than some people give them credit.
I think from an observation perspective as well, these gravity waves can come from thousands of kilometers away from storm track regions or deep convection over land. Makes it more challenging. Jan, would you like to say something?
Yeah, so I just wanted to follow up briefly on on Rob's comments, and I have to agree. I'm not maybe as pessimistic, which is uncharacteristic for me. In fact, I see this actually as a really exciting insight that, and I agree with you. I mean, I'm not saying, for instance, that Erf5 is correct. I say that in this case, it produces the necessary dynamical structure to get the agreement with the observations. Now, to come to your point about the determinism and non-determinism of the system, I think that is a really interesting question, because the reason why the non-determinism or the stochasticity matters is because we have relatively strong non-linearities in the system. If the system was linear, then we could just run a simulation with the average conditions, and we would get the correct result that represents an average of a cloud field, for instance. But that's not the case. We know that these relatively small fluctuations here in vertical velocity, in other cases in let's say aerosol concentration, or maybe even aerosol size and composition, that can lead to relatively large changes. And I think that is a really interesting challenge, something to think about, where we go from there. How do we deal with that? And yes, it is complicated, and it's actually a good thing, I think, that we can't just take the average conditions, run one simulation with the average conditions, and get the result we're looking for. It is a huge challenge, I think, but this is I find this really interesting and motivating and fascinating. And where we go from there, how we deal with this complexity and with the nonlinearity, with the stochasticity. Yeah, and also to follow up on what Graham said, I think to some extent we should have a little bit of faith in these reanalyses data, because yes, observations show that gravity waves can open up pockets of open cells. So there is some grounding in existing observations. Whether we get it correct at this moment, I don't know, but let's see where we go from here, and maybe we will develop better understanding in the future. So I find this really fascinating and interesting.
Yeah, thank you. Thank you for the very stimulating discussion. So I just follow on Rob's question about this. Another question is more like observation about the drop sounds measurements in our Activate campaign. So we do see that actually the if you compare the drop sounds measurements of the Aerosol root analysis, the vertical structure, they're pretty good captured by the Aerosol for our two cases. And if you integrate the divergence, there you get this large scale vertical motion. So that is also pretty consistent. I mean, the structure, not the the fine scales. So the structure is really pretty consistent with this Mirror 2 and the Aero5. But because the resolution of the drop sounds measurements is like about 10 meters, that can really show you the very fine structure of the divergence. But yes, we used this like a time evolving divergence in the simulation because we do see this very strong spatial temporal variation of the divergence from the Aero5, and we also actually see that from our drop sounds measurements as well. So of course we cannot really disentangle the strength and the structure from our simulation yet, but it seems like this, at least these measurements from the drop sounds can shed some light on the structure of the divergence, vertical structure of divergence.
Yutong Zhen?
Yeah, I want to respond to Ian's work about the structure of the vertical velocity on the clouds. I think one way to address this complexity is to start with some idealized simulations, because now I cannot think of any physical intuition about how the geometry of the vertical velocity could influence the clouds, through what kind of pathways. It's very complicated. And therefore, it would be good to start with some very idealized simulations. For example, you can idealize the vertical profiles of vertical velocity. It's top heavy or bottom heavy, and in this kind of idealized settings, it can help you to conceptualize the basic processes about this relationship.
So I see we have a couple minutes left and 81 participants. I don't know if now is a good time to do a photo, or if we want to continue discussing for 2 more minutes and then break for 15.
Yeah.
What do you think?
I suggest that we do it. We do the photo just at the end of the session. But I would like to add one point to this discussion about the covariability between aerosols and dynamics. That covariability is not appears not to be coincidental, but of cause and effect. For example, lower inversion caused by less aerosols, which have caused that has been caused by opening the cells earlier by a passing gravity wave and so on. So therefore, the disentangling is not exactly the right word. This is a whole new conceptual way to think about it. And I will leave you with that.
Danny, that's really the theme that I think we've been pushing for some time now, is understanding this covariability. One can think about it at the system level, for example, within a stratocumulus or shallow cumulus field. One can also think about it at the larger meteorological scales, or synoptic scales, of the covariability of the aerosol along with the meteorology. As Xiaoli was showing today, when you have higher aerosol, what is the meteorology that comes along with that? In a broader sense, there will be case studies where you get some oddities, but I think in the broad sense, understanding the covariability of meteorological conditions with aerosol conditions can really help a great deal in this issue.
Yeah, and how they cause one another.
At the process level, you mean?
Yeah. It's two-way street.
Yeah, yes, of course.
Okay, great. Well, we've now reached our first break, and I think maybe we'll do the photo at the end of the next session. And
now we have 80 participants. Why not now?
Oh, okay. that works for me. So if everyone would turn on their camera, we can get a photo. And I will take a few snapshots. So everyone smile. 1, 2, 3. All right, page 2.
Yeah, you have more than one screen to take. You have to
page 3. Smile. And page 4. Thanks, everyone.
Thank you.
Okay,
So you're welcome to either
minutes.
stay in the meeting. We'll just take a break for 15 minutes, or you can leave and we'll try to let you back in, and we'll be back in 15 minutes at 1/4 to the hour, whichever hour it is for you.
Okay, shall we get started? So the next section is the aerosol effects, and our first speaker is Allison Douglas.
Hi, I'm Allison. I'm here to talk about defining regimes of cloud controlling factors using machine learning, and I did this work with Philip Steer at the University of Oxford. You can go to the next slide. So to define regimes of cloud controlling factors, we took a little bit of an unorthodox approach. So what we did is we trained a light GBM, which is like a type of decision tree machine learning algorithm, on 10 different environmental properties, including aerosol information. And we trained it to predict a cloud fraction. And the output from that light GBM is then the predicted cloud fraction. And also for every point that we use and pass through the light GBM, it gives us weights that define the relationship strength between that cloud fraction and all the environmental parameters that we used. So then we took those weights that define these relationship strengths between cloud fraction and the environmental information, and we applied k-means clustering on the weights to then define regimes of cloud controlling factors. Next slide. So this is just an example of what you get then when you look at the regimes that this type of methodology creates. You can see that off the coast of the Southeast Pacific, you have the light green, which is what we think marine stratocumulus is represented in this framework. And then the yellow regimes are a type of transitional regime out of the marine stratocumulus and into a dark blue, which is what we think a cumulus regime is. And you can also see that the poles have their own distinct regimes from these, which is represented by the dark turquoise or the 13th regime. So this type of methodology does pick up distinct differences in the clouds due to the different factors that control their seasonal cycles and their amounts. Next slide. So for each of these regimes, then we can go through and look at the different controls. So if you remember the map, you can see that the first regime is what we think some type of extratropical convection is, and you can see that that's represented by inverse relationships with sea surface temperature and correlations with AOD. So that regime is driven by decreases in sea surface temperature and increases in aerosol optical depth. And these controls are determined by the weights from the light GBMs. So these are not things that we're prescribing on these regimes or things that we're then going through and fixing. These were all kind of things that appeared after we applied this type of clustering to create the regimes. So the next slide. So if you go back to and look at the warm cloud regimes that I pointed out, you can see that as you move from a marine stratocumulus to the cumulus regimes, the actual drivers of these regimes change. So you go from having marine stratocumulus, which are controlled mainly by the sea surface temperature and the estimated inversion strength, and slightly by the relative humidity in the free atmosphere. And then when you transition into the transitionary regime, it's then controlled by the stability and inversely by the sea surface temperature, because you have the sea surface temperature usually increasing in these regions. And then if you look too at the polar clouds, they're strongly controlled by the sea surface temperature. So then if you go to the next slide. And you can also see that as you move from a marine stratocumulus to a cumulus regime, you have then changes in the cloud properties, including precipitation, which track well with what we know about marine stratocumulus and the transitionary regimes. So you have in the light green, the marine stratocumulus, which has a low daily rain rate, And then as you move into the transition regime, you have a spread in your rain rates going from very low to higher amounts than what you would see in marine stratocumulus. And that's as you get more cumulus forming in this regime, you'll have variations in higher rain rates than what you'd see with just marine stratocumulus. And then as you go to dark blue, which is primarily cumulus, you have an increase in the mean rain rate. Next slide. And then you can see too, if we look at some of the more interesting extratropical regimes, that you have distinct differences in what drives them, even if you don't have the same signatures in their rain rates. So off the coast of China, these mid-latitude storm tracks have the same daily rain rates, but they still have distinct differences in what's driving them, and then also distinct differences in their mean radius from MODIS. So the light purple regime is driven primarily by the instability as you move from the continent off the to the coast, and then the red is primarily driven by like higher aerosol optical depth concentrations and instability that we see with storm tracks. Whereas the dark red, which is further off the coast from these, is more like what you would see with an extratropical mid-latitude cyclone, which is primarily driven by instability in sea surface temperature. Next slide. So when we defined these regimes using the environmental features, rather than the cloud properties themselves, it reveals these regime-specific behaviors that might not otherwise have been seen if you were to just base it on how the clouds appear. And these cloud regimes can be used as constraints to understand the processes occurring within each regime, because they have each of them a unique environmental control. Next slide. Does anyone have any questions or comments?
Thank you, Allison. We have time for one quick question. I think there's one in the chat. Maybe you can answer afterwards. I have a question. I thought this was really fascinating. In this map here, you show these broad yellow regions, for example, off the coast of Africa and South America. Do you see similar controls in these two places on the meteorology, or are they completely different due to maybe biomass burning being quite different or something?
No, you definitely see similar controls. So this was actually supposed to be a GIF before I realized that we were supposed to have a PDF. So this is for January 1st, 2004. But yeah, the yellow regimes here all kind of map onto the same controls. So if you look at them, they have similar strengths in what's controlling the clouds in these regions. And that's kind of why you don't see off the coast of Africa, they don't occur right next to the coast where you might have some aerosol effects, since the yellow isn't really modulated that much by aerosol. But you do see the orange regime, which shows some, I think, relationship with aerosol. So yeah, it definitely picks up signatures of aerosol effects.
Great, thank you. So the next speaker is Isabelle Mccoy. Take it away when you're ready.
Thank you. And thank you to the organizers for their hard work in putting this meeting together. So today I wanted to share a couple of highlights from a recent paper that myself and co-authors published, looking at the influences of recent particle formation on the Southern Ocean environment, and in particular, how recent particles influence the aerosol profiles in that region and the low cloud properties. And so this study is focused on a set of observations that were done in 2018 through the Socrates flight campaign. And this is a photo from that. And you can see that this is a very cloudy region. And there are a lot of reasons that you're interested in the Southern Ocean, one of which is that it's our closest sort of present day proxy for the pre-industrial. And so we want to try to understand what are the aerosol cloud interactions that are in this pristine environment and how they drive low cloud properties and especially brightness. And so for talking about brightness, we're looking at droplet number concentration, or ND. Next slide. So Socrates gave us the opportunity to do in situ sampling of aerosol cloud interactions in the Southern Ocean and to look at mechanisms that are actually critical for setting pristine droplet number concentrations. And so I'm showing you a somewhat simplified diagram of the sort of aerosol life cycle that happens in that region. And this is a life cycle that people have looked at for many, many years and many decades. And so I encourage you in this paper to look at the introduction that goes through some of the literature in this. But in the next few minutes, I'd like to go through and sort of highlight parts of this life cycle that we sort of helped clarify a little bit, hopefully. Next slide. So the first part is this sort of yellow arrow that you see on the left-hand side here. That's the synoptic uplift. And so what we saw in Socrates is that in this environment, you have a huge number of aerosols that are in the free troposphere. And there are especially a large number of very small aerosols or Aiken mode aerosols that's between about 0.01 to 0.1 microns. So smaller than accumulation mode, but they're actually quite critical, as I'll show you in a moment. So we saw this huge number of aerosols. And we also saw that there's a really distinct signature in their air masses. And you can see that in the plot that I'm showing here on the bottom. So the blue are these sort of recent particle formation cases, which is how you're forming these Aiken aerosols. And we saw that there was a very distinct profile in these, that they have a quite rapid uplift. So this is showing you altitude over the last 72 hours. So you can see the blue is a sharper uplift compared to the black, which are non-RPF cases. And so the idea behind this mechanism is that you have these synoptic air masses that are kind of charging through the Southern Ocean all the time. And in the summertime, when you have ocean biology, those air masses at the surface are enriched with DMS and DMS oxidation products. And so the synoptic storm system grab masses and bring them up to the free troposphere. And as they do that, they remove aerosol. And then they kind of release it into the free troposphere where those gases can undergo new particle formation, or in particular at the end of these yellow arrows that I'm showing, that's sulfuric acid nucleation. And so this ends up being really critical for developing this whole kind of reservoir of aerosols in the Southern Ocean in the free troposphere. And I'm showing on the right-hand side, this purple arrow, that these small particles are brought down into the boundary layer quite frequently in large amounts. And they end up being a key source for boundary layer cloud condensation nuclei. Next slide. So in addition to just acting as kind of the source that accumulation mode aerosol grow from, these aerosols actually have another role that we think we're seeing based on these observations. And this is this Aiken buffering mechanism that we proposed, which is a way of maintaining droplet number concentration in the Southern Ocean against precipitation depletion. And so the idea behind this is that you have a huge number of these small particles in the boundary layer, but you also have low clouds that are kind of consistently precipitating, and they're removing kind of accumulation and coarse mode aerosols. So they're reducing the aerosol surface area, which means that you don't have a space for water vapor to kind of condense on as much, and that enriches those updrafts. So you have increased supersaturation in the updrafts in those clouds. And that means that you activate those small accumulation and large Aiken mode aerosols into droplets. And so it kind of pushes back against any sort of precipitation depletion, which would necessarily decrease your droplet number concentration by kind of activating those smaller particles. And you can actually see this if you look at the left-hand side here. I'm showing you kind of two plots. So the panel B is showing you droplet number concentration to accumulation mode number concentration as greater than 0.1 microns, right? So kind of larger sizes of accumulation mode. And that's a scatter plot. And then in panel C, you can see a PF of the droplet number concentration. And so, 2 minutes, okay, thank you. So in these circles, you can see these kind of precipitation depleted cloud features, which is ND less than 10 per cc. And if you compare the Southern Ocean, which is in orange, and the subtropics, you see a lot of cloud precipitation depleted cloud features. You can see that the Southern Ocean doesn't have nearly as much of these precipitation depleted cloud features. So it indicates that these Aiken aerosols are actually having kind of a number of key roles here in setting the brightness of these clouds, right? Because if you maintain your ND, you end up having these brighter clouds. Next slide. So in the kind of final part of this paper, we look to see how well models do at capturing these kind of nuances. And in particular, looked at a set of Camp 6 simulations that were done by Andrew Gettleman and Chuck Bardeen. They were sort of matched to these observations. And we saw that the droplet number concentration low bias in those simulations was associated with underproduction of free tropospheric Aiken aerosols, which led to an underproduction of boundary layer CCN. And so that's suggestive that we need to get these kind of Aiken parts of the mechanism to be right. They exist already, but we need to kind of fine tune them a little bit to get our droplet number concentrations to be consistent with the observations. And so you can see in the plot here, the droplet number concentration bias looking at the PDF, where the thicker line is the observations and the thin line is from the model. So final slide. Thanks. So I'll just leave my kind of summary of points here, as well as a reference for our recent paper and my contact information. And yeah, I think this was a very interesting study, and in particular, it really highlighted for us kind of complicated nature of having sort of multiple sizes of aerosols and how they really play a critical role in this environment. So thank you. I look forward to your questions.
Thank you, Isabelle. We are probably needing to move to the next speaker, so take it into the chat. The next speaker is Tom Gorin, and you can present when you're ready.
Thanks, Matt. So I will show you a relationship that we found between cloud properties that can be observed from satellites that are used to reconstruct or to estimate what would be the cloud fraction and the cloud radiative effect of a given scene, observed scene. So for example, here we have the stratocumulus deck, and the left red curve indicates where the clouds break up. So we use this relationship, apply it on this kind of scenes, and then we say, okay, the clouds would break up where the red line is, assuming some hypothetical cleaner atmosphere. So the next slide, please. The physics or the idea behind this simple model is illustrated here. We have the liquid water path as a function of the effective radius, and the curves are the effective radius profiles for different droplet concentrations, from clean to more polluted. And we define a critical liquid water path, which is the liquid water path at which the clouds start to precipitate, assuming an effective radius of 15 micron. So let's look on the green curve in the middle. The observed liquid water path in black is equal to the critical liquid water path, so the difference between them is 0. But for a more polluted atmosphere, the difference between the critical liquid water path is positive, it's larger, and for cleaner atmosphere, the blue line is negative. And now let's see how this theoretical delta LWP looks like in satellite observations. Next slide, please. So here I show liquid water path as a function of ND, and the color on the background is the theoretical delta LWP, calculated for every combination of LWP and ND. The points are observations from MODIS level 2 that are aggregated to 1 by 1 degree. So every point is colored by delta LWP and cloud fraction. You see a good match between delta LWP from the satellite, from the observations to the theoretical delta LWP that we expect. And also now we see a relationship between delta LWP and cloud fraction. So as we go to the non-precipitating clouds, more blue, the clouds are more overcast. And as we go to more red, meaning more precipitating clouds, the color is, the cloud fraction is lower. Next, please. Now it's the same plot, but I color the observations by the cloud albedo. And we see here a relationship between cloud albedo and the delta LWP. So as we go to non-precipitating clouds, it's more overcast. And as we go to precipitating more red, the albedo is lower. And now we applied this relationship between delta LWP, cloud albedo, and cloud fraction on real data. So next slide, please. This is, we reconstruct now the albedo for 2014, a full year. Let's start with the plot at the bottom. So this is the relationship between albedo and delta LWP. In color is the cloud fraction. And this, we have, you can see the exponential fitting there. It's very robust. So if we, the same relationship, we see it for different years, for different stratocumulus regions. And this relates between the albedo and delta LWP, and we use it to manipulate the data. So let's look on the right figure at the top. This is the observed delta LWP for the observed ND. So where the blue meaning that the clouds are non-precipitating, red precipitating, and in accordance the cloud fraction and the albedo. I see that there is a typo in the title. This is the observed ND. And now let's look on the left figure at the top. Now we calculate the delta LWP, but we assume a lower droplet concentration. So I simply multiply ND by 0.8. So we have a new value for the delta LWP. I use this relationship to tell what would be the albedo for this delta LWP, assuming the lower ND. Next slide, please. On the left side, this is the albedo difference between the clean ND times 0.8 minus the observed. You see that there is a band of larger difference in the albedo. Let's look on the upper right. There we have the observed albedo as a function of the albedo difference. And you can see that the largest difference occurs where the observed albedo is around 0.25. At the bottom right is the relationship between albedo and cloud fraction, and in color is the delta LWP. And this reflectance occurs in the transition between blue to red, or as we saw, between overcast to broken clouds, or between high albedo to low albedo. Next slide, please. This is the cloud fraction difference. It's not the albedo, it's the cloud fraction difference between the clean and observed. And you see the same band over there in the center, and this is actually the reduction in cloud fraction in the cleaner case, and it represents the transition fronts from overcast to broken clouds moves closer to the coast, moves eastward. Next, please. And this is just like the summary and make some conclusions. Let's start with the right figure, right plot. We have the cloud fraction as function of delta LWP. And then you see there are different slopes there. And where delta LWP equals to 0, this is actually where the cloud break up. On the left side, I plot the albedo change in % as function of the mean longitude of the location, the longitude of where delta LWP is equal to 0, where is the breakup of the stratocumulus lex. And you see this that it's actually, we see here that the transition front is being shifted linearly towards the coast as we decrease the aerosol concentration or droplet concentration. So this is true assuming all equal. So no change in meteorology or feedback between cloud and meteorology as was discussed before. In this case, we can use the delta LWP to estimate, as I showed you, the albedo and cloud fraction. And we can, I've been thinking of ways to come up with realistic fraction ND fraction. So not just, hypothetically multiply ND by 0.8, but to relate it to the anthropogenic droplet concentration fraction that it exists in literature. And yeah, and the response of the cloud albedo, as we see here, to aerosol, it does not become saturated with increasing droplet concentration. This is due to the larger coverage of the clouds, and in contrast to the Toomey effect, which is saturated as we increase the aerosols. Thank you.
Great. We have about a minute for questions. Would anyone like to raise their hand? Duncan.
Thanks, Tom. That's really, really nice talk and neat result. Have you tried looking at these relationships in any models at all, or in LES simulations? Did they?
I used LES just to see if it behaves similarly. So I did the same analysis to Lagrangian trajectory, LES, a similar concept to what Jan showed earlier. And we see the same relationship, but because it's Lagrangian trajectory, we see it like a sharp decrease from the breakup occurs at at once the clouds break up. So we don't see this structure, it's smooth scatter plot as we see here on the right side. But it behaves similarly. If I would take many LES, I assume I will get the same. But the physics is there also in the LES, yeah.
And the relationship is the same, the LWP. Yes. Well,
yes.
Neat.
Yes.
Cool. Thanks.
Thanks, Tom. We'll move on to the next speaker, Shang Wu.
Hello, can you hear me?
Yes.
Oh, thank you. Good evening. My name is Shang Wu.
I'm from Nanjing University of Information Science and Technology. Today I'm going to talk about some of our recent work, effects of aerosol number concentration on micro and microphysical properties in shallow convective clouds. Many thanks to my co-authors, Zhou Yin and Professor Lu. Next, please. The dispersion effect. Dispersion effect is the influence of aerosol number concentration on the shape of the cloud droplet size. Liu and Daub find that the magnitude of the first indirect aerosol effect can be reduced by 10% to 80% due to the dispersion effect. In recent years, some studies point that vertical velocity and entrainment are significant influencing factors of the relative dispersion. The first slide, please. The next, please. Okay, thank you. In our study, the first scientific question we're concerned about is how does aerosol number concentration affect vertical velocity entrainment and cloud fraction? Next, please. Given the small cross-sectional area of shallow convective clouds, we use the Wolf model with the built-in larger Eddy simulation module. The cloud condensation nuclei are calculated by the empirical power law expressions shown at the bottom of this page. To simulate the clouds under different aerosol number concentration, we set the value A to 100 and 50, 500, 1000, and 2000 per cubic centimeter, respectively. Next, please. As we can see in figure A, the increased aerosol number concentration can enhance the mean vertical velocity. However, figure B and figure C show that both the sum of updraft and downdraft decrease with the increased aerosol number concentration. From figure D to figure F, we can see that as the aerosol number concentration increases, the downdraft grid number decreases faster than that in the updraft. In conclusion, it is the decreased downdraft grid ratio that enhances the mean vertical velocity. Next, please. This slide shows the effect of aerosol on cloud fraction. From figure A to figure D, we can see that as the aerosol number concentration increases, the cloud fraction decreases gradually, especially in the upper part. More aerosol can reduce the mean radius of cloud droplets, thus accelerating the evaporation of cloud. Next, please. We use the adiabatic function to reflect the strength of entrainment. The equation of adiabatic function is shown in the upper right. The larger the adiabatic fraction, the smaller the entrainment. From the figure in the left, we can see that as aerosol number concentration increases, the adiabatic function decreases, since the vertical velocity enhances with the increased aerosol number concentration. The mixing time between cloud parcel and the surrounding air within a unit distance is shortened. A shorter mixing time can cause a larger adiabatic and smaller entrainment. Next, please. The second scientific question we're concerned about is what are the combined effects of aerosol vertical velocity, entrainment, and cloud fraction on relative dispersion. Next, please. As we can see from the figure in the left, the effect of aerosol number concentration on relative dispersion has vertical spatial variability. In the second area, the complex relationship between relative dispersion and the aerosol number concentration is caused by enhanced condensational growth and activation process in the second area. The decrease in relative dispersion is related to larger vertical velocity and weaker entrainment in the first area. As aerosol number concentration increases, the relative dispersion increases faster with height. We guess that this feature is related to the entrainment process, but we don't yet have a good explanation. More in-depth study will be done in future work. Next, please. For the area 2, we think that the change in cloud fraction is another mechanism to reduce relative dispersion. Through this cartoon, we illustrate that compared to the clean condition, evaporation is stronger in the boundary of polluted clouds, thus causing a smaller relative dispersion. Next, please. Here is a summary of the main content. Well, time is running out. One of the important things is the effect of aerosol number concentration on the vertical spatial variability of relative dispersion. Vertical velocity entrainment and the cloud fraction have different combined effects on relative dispersion in different areas. Well, thank you.
Looks like we have time for one quick question if there's any. Raise your hand. Okay, I think we'll maybe stick to the schedule, and now we move to Haruka Hada for the last 6-minute presentation from this section.
Okay, can you hear me?
Yes.
Thank you. I am Haruka Hotta from University of Tokyo. My presentation title is Aerosol Effect on Warm Clouds in a Global Cloud System Resolving Model, Sensitivity to Microphysics Schemes. Next slide, please. It's been a problem that GCMs tend to overestimate the effect of aerosols on cloud water content compared to satellite observations. A previous study showed that a global cloud system resolving model, NICAM, reproduces satellite-observed liquid water path responses to aerosol. NICAM with explicit representation of cloud microphysics offers a new opportunity for aerosol-cloud interaction studies. The cloud microphysics scheme NSW6 in previous studies is one moment scheme and lacks the full prediction of number concentrations. So this study focuses on how cloud microphysics affect aerosol cloud interactions. Next slide, please. We conducted NICAM simulations with two different microphysics, NSW6 and NDW6. We adopted the same schemes for autoconversion and accretion to focus on the difference between one-moment microphysics and two-moment microphysics. Now I'd like to move on to results. Please look at the figure. We evaluated the aerosol effect on clouds using the liquid water path and cloud number concentration relationship. NDW6 shows a weaker correlation than NSW6, consistent with satellite observations, while the aerosol effect is weakened in NDW6. Next slide, please. We compared rainwater characteristics in NSW6 and NDW6. NDW6 produces a larger number of raindrops. So NDW6 contains more rainwater because the falling speed of rain is lower. As a result, the ratio of accretion to onto conversion is higher in NDW6. By such a mechanism, aerosol effect is weaker in the previous slide in NDW6. And we used radar observations to evaluate the microphysics of rain. NDW6 provided a more realistic transition of rainfall profiles. NDW6 provided a realistic transition of rainfall process. Next slide, please. Okay. In order to verify the effect of raindrop size, we conducted a sensitivity experiment with modified raindrop parameters in NSW6. In NSW6 with smaller raindrops or with the slower falling speed, the ratio of accretion to autoconversion is higher and the aerosol effect is weak, as you can see in the bottom figures. These results suggest that the size of rainwater affects the aerosol effect through the following mechanism. When the raindrops are small, clouds contain more rainwater, and which causes a higher accretion rate and a weaker response of clouds to aerosols. Next slide, please. Okay. Let me summarize the presentation. Become NDW6 shows the weaker aerosol effect on liquid water paths than NSW6. Smaller raindrops in NDW6 allow the precipitation process to be more consistent with observations. The size of raindrops is likely the main factor of the difference between NSW6 and NDW6. Thank you for listening.
Thank you, Haruka. Are there any questions? We have a couple minutes.
Why is higher?
There's a question in the chat from Andrew Williams.
Oh, okay. The question is, why does higher autoconversion lead to a weaker response to aerosols?
Oh, okay. Yeah. Because so yeah, I think aerosols increase liquid water path because when there is more aerosols, autoconversion process is decreased. I mean, through autoconversion process, aerosols increase liquid water path. And that's why higher autoconversion brings a weaker response to aerosols. Yeah, does it make sense?
Andrew says, I think it's accretion that increased relative to autoconversion. I had a question that relates to the entrainment in the model. Is there any parameterization that accounts for the evaporation of the cloud changing as a function of droplet size or influenced by aerosol? I know this draws on earlier work by Sato looking at different entrainment parameterizations.
Okay, thank you.
Okay, thank you. We are 1 minute ahead of schedule, so I think we can maybe just continue onwards to provide more time for discussion. So now are the 2 minute research highlights. And we will begin now.
Great. Can you hear me?
Yes.
Great. Thanks, everyone. My name is Siddhant Gupta. I am working at the University of Oklahoma with Greg McFarquhar. I'll quickly show some results from observations of marine stratocumulus clouds over the Southeast Atlantic Ocean, where we see variable above and below cloud aerosol concentrations. And I should acknowledge my co-authors here as well for their contributions. Next slide, please. So I'm showing observations from the NASA Oracle's field campaign, where flights were conducted off the coast of Africa, which sort of is shown in the map to orient you over the Southeast Atlantic Ocean. I will be showing results from about 300 profiles across 24 research flights. And I divide each cloud profile into two categories. A, the contact profiles, which are in blue, which are clouds which were in contact with above cloud biomass burning aerosols. And I define that as aerosol concentration greater than 500 per centimeters cubed within 100 meters of cloud top height. And the other type of profiles is separated profiles, which have a separation in the vertical space between the aerosol and the cloud layers. Next slide, please. This is just my final slide, which sort of summarizes the differences between the contact profiles and separated profiles. Based on the aerosol indirect effects, as we would expect, we see higher droplet concentrations and lower effective radius in the contact profiles. In the images on the right, I'm showing the vertical profiles of droplet concentration and effective radius. And as we would expect with the Toomey effect, this leads to higher optical thickness for the contact profiles. These results are summarized in a publication in ACP. And then for the second part, I looked at macrophysical properties of these profiles, looking at rain rates and also precipitation susceptibility. And I find that contact profiles undergo precipitation suppression. They have about half of the average rain rate compared to separated profiles, and they also have lower precipitation susceptibility. In the interest of time, I haven't included any sensitivity tests that I conducted based on below cloud aerosol conditions and meteorological conditions, looking at low tropospheric stability and estimated inversion strength. I can address any questions based on that or have more discussions offline. And finally, I just wanted to mention that I am looking for postdoctoral positions. So if anyone has any leads, that would be appreciated. Thank you.
Thank you, Siddhant. Jianhao Zhang, are you able to go next? Are you muted? Ah, there.
Okay. Is my voice okay?
Yes, I can hear you.
Okay. Yeah. So hello everyone. In this study, we are trying to quantify the low cloud radiative susceptibility to NG perturbations over the Northeast Pacific region in a way that the frequency of occurrence of the changing meteorology and cloud states are accounted for. This is important. For example, if you look at the figure on the left, the formation of drip tracks is actually very highly dependent on the cloud states and the changing meteorology. So moving on to the figure on the right, here I'm showing you the calculate albedo susceptibility from series modus observations indicated by the color of the circles in this liquid path ND space. And the frequency of the occurrence of this particular cloud states is indicated by the size of the circles. So here we identify three regimes. First, for the precipitating clouds, we see this brightening potential. And then moving on to the non-precipitating clouds, we see a darkening regime associated with deeper non-precipitating clouds. And for the thinner non-precipitating clouds, we see this Toomey-dominated brightening regime. So for each regime, I further calculate the averaged radiative susceptibility, which is the albedo susceptibility times the incoming solar radiation and the cloud fraction. and weighted by the frequency of occurrence of each cloud state. So we arrive at the total weighted forcing per ND perturbation of about 21 watts per meter square per ND perturbation. So this is the overall cloud brightening potential for the region. Next slide, please. So here I'm just trying to highlight the cloud top has a strong impact on the overall radiative stability. So if you look at the figure from left to right, this is the quartiles data grouped into the quartiles of cloud top highs. And the striking feature of this figure is a strong decrease in radiative susceptibility from 60 to -40. And we offer two reasonings for this dramatic change. First of all, is the magnitude of the susceptibility is strongly decreased, especially in a darkening regime. As you see, the brownish color gets strong enhanced. This is because the deeper clouds, we expect stronger cloud top entrainments. And on the other hand, we also see a strong shift in the frequency of occurrence of the cloud states, which is towards the darkening regime. You see the circles of the darkening regime is getting bigger as the cloud top increase. So together they explain this dramatic increase. That's all I have. Thanks.
Thanks, Jianhao. And last but not least, Hao Wang.
Hello, can you hear me?
Yes.
Okay. Hello, everyone. I'm Hao Wang from Nanjing University, and my topic is the cloud water response to aerosols in CSM2 with improved treatment of subgrid cloud variability. Representing the subgrid variability of cloud properties has always been a challenge in GCMs, and in the macrophysics schemes in GCMs, the effects of the subgrid variance of cloud are usually accounted for by scaling the process rates by an enhancement factor, EF, that is derived from the subgrid variance of cloud water. And in our study, we find that the EF derived from cloud in CSM2 is severely overestimated in most of the oceanic areas. This leads to the strong overestimation in the autoconversion rate, which represents the speed of the collection of cloud droplets consuming the cloud water. Through an EF formula based on the empirical fitting of models, we improve the EF and the autoconversion rate in case EMP, and set the default case to compare the effect of EF on aerosol cloud interaction. To evaluate the marine single-layer liquid cloud response to aerosol, we use the cloud droplet number concentration, CDNC, to show the change in aerosol and classify the data into different cloud geometrical synchronous bins to control the meteorological conditions. As is shown in the picture, the slopes of the lines show the sensitivities of the macrophysics processes and the liquid paths to aerosol. The EF tends to be most severely overestimated when the cloud fraction and the CDNC are small, where the subgrid cloud is more inhomogeneous. So after changing the EF, the autoconversion rate with relative smaller CDNC decreased most, and the mean slope decreased too. The total conversion rate means the autoconversion plus the accretion, and the latter one represents the collection of the cloud water by raindrops. The change in the sensitivity of total conversion rate is controlled by the change in autoconversion. And as a result, the sensitivity of liquid path to aerosol, which is always overestimated in GCMs, decreases and are in better agreement with models. The improved sensitivity shows the large effect of the subgrid cloud variability on the aerosol cloud interaction in the global climate models. And that's all. Thank you.
Thank you. And actually, we have one. Sandip Pal, would you like to go next?
All right, can you hear me?
Yeah, sorry.
Okay, yeah, I'll mute there. Thank you for arranging this last talk here. And myself, Sandip Pal from Texas Tech University. This is the work actually a student has been working on. So to find out some of the frontal modification of the atmospheric boundary layer depth characteristics over land surface. So that's pretty much the nutshell, the work plan here. Next slide, please. So if you consider the traditionally boundary layer itself has been traditionally explained with respect to the local surface fluxes itself, and there's in most of the studies that has been considering that under horizontal homogeneous condition that is actually basically neglecting the advection. However, advection neglection is basically not unwarranted for most simulations for the real boundary layer. So here in this work, we are challenging that atmospheric boundary layer depth modification is actually governed by combination of the local fluxes as well as the advection itself. So in a sense, latter is basically the advection of the entire boundary layer is modifying within let's say assume the frontal system. Next slide, please. So if you imagine that 3 to 4 times of extreme scenarios, if you know the local fluxes, we talked a lot about the urban-rural interface, land-sea interface, complex terrain and adjacent plains. One thing that has not been taken a lot of attention was that how does the mid-latitude cyclones affecting the ABL processes? So for instance, when a frontal system comes, how does the boundary layer itself modifies? So in essence, the question is how weather system modify the atmospheric boundary layer characteristics and vice versa, and what are we missing? And in a sense, basically, we're trying to find out the impact of another air mass, because as the frontal system comes, it is basically air mass exchange happening. So you're not basically studying the local cell process, but also the transported process itself. Next slide, please. So to do that, we actually consider the radio sound measurements at zero reducing, that is kind of daytime measurements over the United States. We actually selected around 18 sites, that is air from the mountains, air from the coastal regions, and away from the major urban locations. So as you can see in the lower left panel here, these are the sites that is a schematic of the frontal surface map here. So how does the front passes? So you can actually think about, when the frontal system is closed, when the frontal system is nearby, you can basically traditionally explain the warm sector versus cold sector processes. And people have been working on a lot on the over the ocean surface. How does this boundary layer modifies, but nothing has been worked on the boundary layer depth over land surface. So upper panel shows during summer that how does the moderate distance prefrontal and near distance prefrontal sampling looks like, and the right two panels looks like how does the postfrontal characteristics looks like. So we found that warm sector boundary layer depth was actually bigger, deeper than the cold sector boundary layer depth, as well as we found the same with respect to the winter. And however, the contrast in the boundary layer depth in winter was much more stronger and much more deeper itself. So that is actually makes sense, because the frontal strength in the winter over the land, in particular over continental US, it's much stronger. That is actually that using this data set, we actually pretty much made a very simple hypothesis here and showed that air mass advection needs to be considered. And that's pretty much we submitted these manuscripts very recently. And thank you for your attention.
Thank you, Sandeep. Okay, great. Thank you all the speakers for being timely, and we've now reached the discussion and next steps, and I will hand it over to Andrew.
Okay, thanks, Matt. And I'm wondering if people have any comments. So once again, just raise your hand and we can unmute you. And we'll launch into some discussion of the talks we just heard. And then I think we may try to have a little summary at the end to try to link things together. I think I was very interested in some of the comments we saw up. Let Rob go.
Hi, yeah. So I had a question that kind of relates to talks from both sessions. The work that Jian Hao presented on the susceptibility and was looking at quite different, at least it seemed to me that there were quite different control variables in the Northeast Pacific from those in the North Atlantic that Xiao Li presented about when the albedo of the cloud changes sign from positive to negative in response to increasing droplet concentration. So I wonder if there's any thoughts about that.
Hi, Rob. Thanks for the comments. Actually, so in terms of Xiaoli's presentation, I don't think she showed the susceptibility in terms of liquid parts and ND space. I think she mainly showing that as a function of different meteorological controls. But however, I think she did arrive at overall negative susceptibility for the region, which means cloud darkening potential. And I think that's whereas I'm arriving at the overall brightening potential, I think the difference is coming from the higher occurrence of the higher clouds, deeper clouds in the North Atlantic region. Maybe Xiaoli has more comments on that.
Hi. So Rob, are you? So you're referring to the different meteorological conditions that Jianhao found higher boundary layer height corresponds to more darkening cloud. Is that where you think it's inconsistent? No, we cannot hear you.
Yeah, sorry, I muted myself again and then I can't unmute. So no, I'm not saying they're inconsistent. I just thought it was interesting that you looked at it in a very different way. So I was curious if there is the extent to which they are consistent or inconsistent.
Yeah, so from what hi, from what I see, so in the North Pacific regions, the SST variability is weaker. It's actually much weaker than the SST variability in the North Atlantic. So we don't see a very strong signal of the SST-dependent cloud aerosol susceptibility. However, over the North Pacific regions, there is a strong signal of the cloud top height, of the boundary layer height dependent clouds albedo susceptibility, and I think the increase of that boundary height is dependent on other factors other than the SST.
Other comments or questions from today?
Yeah, I would like to say something.
Go ahead, Danny.
We have seen that there was one presentation showing that the opposite susceptibilities under different regimes, and I like that presentation, especially compared to another presentation showing the effect of aerosols on convective clouds near Florida, which showed only the negative branch of the susceptibility. And if one looks just this way, then one doesn't get the full picture. So in my view, in any study that attempts to have input to global calculations of the forcing, one needs to look at the full range of the parameter space and the sometimes opposite susceptibilities, and on application to the globe, take this into account.
So Danny, you're referring to Allison's talk with the global analysis. Is that what you're talking about with the different cloud governing factors? I forget what the term was.
Right. Mm-hmm.
Yeah, I thought that was very interesting, the bringing the weights and the clustering to bear on understanding what sort of governed the cloud fraction. I guess one question on that maybe for Allison is what happens if you look at variables? I mean, you focused on the cloud fraction, as I understand. Have you looked at variables beyond the cloud fraction? Let's see if we can unmute Allison here if she wants to comment.
So I have looked at cloud optical depth, I think the most in-depth, other than cloud fraction. And it has, so the way that we found regimes was just using, it's called the Albedo method. So it's determined by the k-means clustering algorithm. And cloud optical depth had less regimes than cloud fraction. But when we combined the cloud optical depth with the cloud fraction weights to then find regimes that consider both of those relationships, the regimes didn't change much. So it seems like cloud fraction captures maybe some of the variation you see in other cloud properties, but that is something that we want to look into is if you use the same framework for like liquid water path or cloud top height, how those also differ.
I have a comment on that, but I'll let Graham go first.
Another question to Alison. I really enjoyed the talk, Alison, and I was thinking about, some of the older ways of looking at this problem with metrics like lower tropospheric stability as a means of predicting cloud amount. And, you've got a much more sophisticated predictive method. And I just wondered how those compare. Can one lump all these various meteorological cloud controlling factors into some sort of metric like LTS or similar as a predictor of cloud amount, and whether you've compared your method with the sort of traditional simpler ones?
So we haven't exactly compared using just LTS, but we have looked at like some of the relationships that like between LTS and SST, and then comparing it to like other older methods that just use a single predictor for cloud amount. And you see the same relationships come out of this. So you see that LTS, or well, we use EIS, which is included in EIS, that you have for certain regions the same like correlation between increasing EIS and increasing cloud amounts. So it's almost like this, our framework is inclusive of like historical methods, because you can then pick out for each variable and find like the historical trends between cloud amount and that particular environmental feature. But I don't think it would be possible to make one single metric of all of these environmental parameters, just because all of the relationships aren't strictly positive. So it's because you have for each environmental parameter, it can be positive or negative in a varying strength. So it'd be hard to make one metric based on all of them.
Right, and I was, of course, thinking more about stratocumulus rather than your global cloud map. But anyhow, I just wanted to commend you on that work and just raise some discussion around it.
Yeah, I was sort of interested in the commonalities between what Alison was talking about and what Tom Gorn was talking about with the regimes and the cloud fraction variability, because it seems like there's some commonality even in those metrics there between looking at variability in liquid water path and cloud fraction and some of the things that Alison was also seeing. There may be some ways of looking at that both from the large scale and the more detailed scale that Tom was looking at in some particular regimes. Other comments? Chi-Wen.
Hi. Yeah. I have a question for Sandeep, which is about you mentioned that the overall interface and non-C interface, they affect the boundary conditions, but they are also associated, all these interfaces, they are also associated with strong Aerosol contrast. So also, as we know, Aerosol impact on the boundary condition, boundary layer properties a lot. So did you have a plan to look at the Aerosol impact as well? I mean, Rallo, I saw you a lot look at that, but I think they are very related, and also because related to the our Cheson field campaign over the Houston.
Yeah, That's a great question, Joan. You know, like we just reporting the first time that with respect to this frontal modification of the boundary layer depth over land. So that has not been worked out before. So we the question with respect to the aerosol mixing, you know, the boundary layer depth itself not only the triggers the aerosol mixing but also other tracer mixing as well. So there's many other parameters. So in the manuscript we have also results about how does the potential temperature and the mixing ratio, water vapor mixing ratio changes in the two sectors. So we know those meteorological variability has been traditionally worked out for last 200 years, you know, that people have been working on the frontal modification itself. But, you know, with respect to the boundary layer features, how does it actually consider? So that is pretty new. And we're reporting the observed variability over like for 5 years period. That is map is averaged over the region for the 18 sites and for winter and summer. Aerosol measurements in those sites would be pretty interesting, and we can actually connect. That is you know, I am working on also in parallel research, you know, using just because these are instantaneous boundary layer depth measurements. We don't have the truth of the real frontal modification. So we are actually also working in parallel with the aircraft observations. So we flew across the frontal boundary in different heights using LiDAR observations. So those will be important to correlate the aerosol backscatter and aerosol extinction and the boundary layer properties, as well as you know, other thermodynamic variables across the frontal boundary. So that's pretty much will be coming up, not yet has been done. But this is pretty much making the grounds for future work itself, because this is a framework we try to establish. How does the frontal modification of thermodynamic properties has been worked out? Now is basically asking the same question for, you know, boundary layer depth variability across the front. So your answer to your question is yes, we are interested, we will be doing, but we have not done yet. So that's pretty much I would like to say at this point.
Thank you.
Thank you. Any other questions or comments? So I might sort of bring the discussion outward to sort of a sort of summary of the day, which I thought was interesting between the sessions. I thought we saw a lot of discussion and this was something we talked about a little bit earlier, the coupling and processes. So the aerosols and dynamics for shallow clouds, and that came out again today in the second part. And I think what we've really seen is that there's a lot of interesting and diverse tools being brought to bear on this. And that ranges from satellite data and global analyses to working with global models to working with LES, and some are global analyses, some are different regimes. And it's interesting to see, you know, can you take the things we're talking about with the details of the dynamics and some of the work that we saw with looking at LES and liquid water path and thresholds, and relate that to some of the analysis that's happening at the large scale, either through satellite observations or even some of the modeling studies where the satellite observations are being used to constrain the bulk models in different ways with various, or even looking at some of the LES simulations in particular regimes. So it's interesting that there's a lot of different, we're still not quite bringing everything together, it seems, and there's a lot of information and tools that could be brought to bear on that. And I'm wondering if people have thoughts about, as we think forward with ACPC, how there are different ways of moving forward together, or doing some different comparisons between the different studies that people are doing.
Natural experiments, of course, is something that is of prime interest, but that will be a subject of tomorrow's session. It's too early to summarize.
There is, but we have seen some of that today. And so, but that's a good segue, Danny, that, you know, experiments or natural perturbations, and people are doing that. You know, we saw some of that work, and people are compositing either using observations, or they're doing it in a hypothetical way with changing aerosol concentrations. Philip.
I fully agree with you, Andrew. There are new techniques, and we apply them to some bits, and we have lots of models in some other bits and other regimes, and to bring this together would be quite quite interesting, particularly the analysis, for example, that Alison showed with these sort of cloud controlling factors from satellite data. Nothing stops us from doing that with model data, and we will do that already. But I think we can learn quite a bit by comparing the satellite with model data. And it's sort of a different because it's so multidimensional. So it includes so many different controlling factors. Well, in the past, as Graham said, we followed physical intuition and what we think is right, but maybe there's also some surprises. I think we learn a lot, but some coordination at some point could be quite useful.
Right. Well, there is this discussion that some of those on this call were a part of this potential Aerocom cloud perturbation experiment, looking at clouds and aerosols. And it seems like if we can get the fields in there for that experiment to do the analysis you're talking about, that's a good opportunity to do a multi-model comparison with the large scale models. I mean, it'd be interesting. And I guess the other thing is to think about doing what Alison's done with the smaller scale model in different regimes. I don't know if that's been considered or if it's already been done.
Thinking about it, but I mean, one thing that ACPC, I mean, what we could really discuss at some point, I think, if we wanted to link ACPC a bit more closely with some of the global modeling bits and specifically do similar analysis to what we want to do maybe in Aerocom to the more high resolution and process-based models. I think to link this up would be a real progress because at the moment we're still going parallel, but not joined up.
So to Andrew's point and all of these points, these are really good points, but I think there's a fundamental challenge that we face, and that is the fact that we've got these large disparities in scale between a large eddy simulation and a regional model and a global model. The ability of these different models to resolve processes, and then of course the inability of the small scale models to resolve the circulations at the larger scales. And tying all this together is probably one of the biggest challenges we face because we learn a lot from LES, and yet we can't really project that onto the larger scales. We've got the larger scale simulations that really point us in interesting directions, but they don't resolve the processes that we care about. A good example perhaps being the liquid water path adjustment question. You know, how do we resolve the liquid water path adjustment question, which is a huge one. And the scale at which one does the analysis, I think, is particularly important. So I'll leave it at that and see if there are others who want to pick up on this.
Well, I would like to say that we saw in the presentation of Kenta the huge discrepancy between any model simulations of of the drizzle and rain and cloud water compared to CloudSat, and we are just not there yet. If we first need to do that, right? The basic parameterization like KK is not what we really want.
Right. I think that's a good point, Danny. And I think to Graham's point, if we can figure out, as you were saying earlier, Graham, what the key covariances are, we can then evaluate, are we seeing that at the large scale? And I thought it was very interesting that some of the large scale analyses were driving well the small scale models, and that was actually, was the small, that you were getting the right structure of, say, vertical velocity perturbations at the small scale just by having some of the larger scale information. And there was some, it's not clear why that works, but there maybe is some feedback between those scales. But I kind of think the adjustment should be tractable if we can figure out where we're failing. And it may be in the warm rain process, and it may be in the linking that process with various other pieces. But yeah, I mean, these are all, I guess, trying to think about this offline and bring this together may be a place where we can all try to make progress. Any final thoughts as we come up on the top of the hour? It's been an intense couple hours for everybody. And we'll have a chance to come back to this tomorrow. So tomorrow we'll talk a little more, as we said, about some of the natural experiments and perturbations that people are studying and different ways to do that on various scales, and that may provide another perspective on this in a different way. Any final comments, Matt?
No, I think this has been a fantastic session, and looking forward to having a repeat of this again tomorrow, but slightly different topics.
Anything else, Danny or Mingwai, that you want to say before we close?
Just I would like to remind everyone that you can have like a virtual poster or additional presentation to upload. And Mingwai, please send to everyone how to access that so that we can benefit also the more one-on-one interactions. If you want.
Yeah, we will do that. And let me see. But I think we checked. Not many people really upload some of the supporting materials.
That's why I want to encourage and to remind people that this.
Yes. Okay. I think once we receive it, we probably will share it either through the Zoom or some other ways. But I think I just want to bring a point. Should we? I mean, how do you think about today's the session without any pointer? Do we want to make any changes or encourage people to use the annotation, or we think it's totally fine? We just leave it the way it is.
The annotation is useful. Unfortunately, nobody uses it. I definitely intend to use it, and hopefully others will follow.
I saw that.
Yeah, I think it's working pretty well. If people want to use it, they can figure out how to use it. We can do that. But I also wanted to thank, in addition to Matt, a couple of people behind the scenes who've been helping out today. So Viola Toll and Michael Diamond, who've been helping take notes, and Yi and Kao Yang, who have been helping share the presentations along with Dan Grosvenor and Franziska Glasimir. So thank you very much for all your help in helping things run very smoothly today, and we really appreciate it. And I think we'll see everybody tomorrow, hopefully.
Yeah. I second the thank you, and looking forward to the second day.
Yep. All right. Thank you very much. And I'll stop all the recording and shut everything down.